Good morning, everyone. My name is Jairam, and I'm here today with my team to present our project on implementing LCW compression algorithm. Our team consists of 4 members, including me, Jairam, Shrikar, Dhanaram, and Tarakeshwar. We're all MSCA students of class 5800. Our project focuses on the need for efficient data compression techniques as the size of data generated by the modern computer systems continues to increase. To address this challenge, we explore the LCW compression algorithm and work collaboratively to develop an efficient implementation. In this presentation, we'll share our experiences, discuss the algorithm's technical details, and showcase our implementation. We have outlined the agenda for today's presentation. This will cover the following topics. We'll start by introducing our project by providing the background information on the compression algorithm. We'll discuss the need for efficient data compression techniques and the challenges of handling large volume of data generated by the modern computer systems. We'll dwell into the technical details of the algorithm, its advantages over other compression algorithms, and showcase our implementation and its performance. Finally, we'll summarize our project's key takeaways. So without further ado, let's dive into the presentation. So LCW is a lossless data compression algorithm that have been widely used for many years. It was first introduced at 1984 and has been widely adopted due to its high compression ratio and fast decompression time. In this presentation, we'll explore the algorithm, its implementation. We'll discuss the various components of the algorithm, how they work together to achieve efficient data compression. Additionally, we'll highlight the benefits of the LCW compression, its application in various fields, including file archiving and data storage. Overall, this presentation will provide a comprehensive overview with significance. As a team, we have put in significant amount of effort to understand the intricacies of algorithm and have worked collaboratively to develop an efficient implementation. We're proud to have successfully implemented it and excited to share our findings and experiences. Our motivation for this project stemmed from the need for efficiently compress large volume of data generated by the modern computer systems. With the increasing amount of data being generated by the various applications, file sizes have been growing significantly, making it challenging to store them, transmit them quickly and efficiently. This problem is especially acute in applications such as image and video processing, where large file sizes can lead to long processing times, increased storage requirements. To address the challenge, we sought to explore and implement the LCW compression algorithm, which has provided to give high compression ratios while maintaining the original data's integrity. Our project's ultimate goal was to contribute to the development of efficient and robust compression algorithm that could overcome the challenges of handling the large volume of data in modern computer systems.
Before we dive into the details of data compression, let's take a moment to understand why it's so important. In today's world, digital data is being generated and consumed at an unprecedented rate. From emails and documents to images, videos, and music, we rely on digital data for our work and leisure. However, digital data can take up a lot of storage space and it can also be time consuming to transfer, especially over slow or unreliable networks. That's where the data compression comes in. It enables us to reduce the size of digital data without losing any important information, making it easier to store and transfer. There are two main types of data compression, lossless and lossy. Lossless compression algorithms work by identifying patterns or redundancies in the data and replacing them with more efficient representations. Some common lossless compression methods include Huffman coding, Lempel-Ziv-Welch encoding, and run-length encoding. Lossy compression methods are often used for multimedia data, such as images, audio, and video, where some loss of quality may not be noticeable to the human eye or ear. Popular lossy compression algorithms include JPEG for images, MP3 for audio, and MPEG for video. As technology continues to advance, the need for efficient data compression will only grow. By understanding the background and fundamentals of data compression, we can appreciate the value of it brings to our daily life and the role it plays in shaping our digital future. Now that we have an understanding of what data compression is, let's take a look at the problem statement that drives research in our project. The problem statement for our project can be defined as follows. How can we define and design an efficient compression algorithm that achieves maximum compression while minimizing the loss of data quality? And how can we optimize the compression process to improve storage efficiency and data transfer rates? This problem statement encompasses the key challenges associated with data compression. One of the main challenges is balancing the compression ratio with computational requirements. In other words, achieving maximum compression while minimizing the computational resources required to do so. Finally, it's important to ensure that the compressed data remains useful and meaningful for its intended purpose. This can be a difficult balancing act as compression techniques may remove information that is considered insignificant or redundant, but that could be important for certain applications. Now that we have a clear problem statement for our project on data compression, let's explore some solutions. One of the most efficient ways of data compression is the Lempel-Ziv-Welch algorithm, which was introduced in 1984. LZW is a lossless data compression algorithm that works by replacing frequently occurring sequences of data with codes which are then stored in a dictionary. During the compression process, the dictionary is built dynamically and shared between the compressor and the decompressor. This allows the decompressor to reconstruct the original data from the compressed data without any loss of information. The output of the LZW compression algorithm is a sequence of codes that represents the compressed data. The compressed data can be stored more efficiently than the original data because the codes are generally shorter than the sequences of characters they replace. The decompression algorithm uses the same dictionary as the compression algorithm to reconstruct the original data from the compressed data without any loss. Overall, the LZW algorithm is a powerful tool for achieving efficient and effective data compression. It's used in wide range of applications from file compression softwares to image and video compressions. By leveraging the power of algorithms like LZW, we can improve storage efficiency, enhance data transfer rates, and reduce the computational resources required for data compression.
Well, it works simply using an encoder and a decoder. So when you first give a file, it will be compressed using an encoder, and this file can be easily transferred as it's of smaller size now. And then we can decompress it using the LZW decompression algorithm. So now let's have a deeper look of how LZW works. So one of the key benefits of LZW compression is that it can achieve compression ratios of up to 60% or more for certain data types, depending upon the degree of redundancy and the size of the symbol set. This means that we can significantly reduce the size of our file without losing any data, and also making it easier and faster to transfer or store them. Another advantage of LZW algorithm is that it can be implemented with a relatively smaller amount of memory. This makes it suitable for use in embedded systems and other resource constrained environments where memory is often very limited, and it plays a crucial role. The memory footprint of LZW compression can lead to a faster processing times, which is particularly important for real-time applications. Overall, LZW compression is a widely used and effective method for lossless data compression that can be applied to variety of data types and applications. It can be used to compress text, images, and other data types, make it versatile tool for data compression. And with its ability to high compression ratios and its low memory requirements, LZW compression is a valuable tool for anyone who's looking to optimize their data storage or transfer. Now let us have a look at the algorithm. So now if we take a closer look at the LZW compression algorithm, there are six steps involved in it. Initially, we initialize a dictionary with all possible character codes. This means that each character in the input data is assigned a unique code. Now we read the input characters in a sequence, and this data that we want to, this is the data that we want to compress. We find the longest sequence of characters that match a code in the dictionary. This code, this is the core of the LZW algorithm. It identifies the repeated patterns of the characters that can be replaced with shorter codes. Now we output the code for the sequence of characters. Once we have identified the longest sequence of character that matches the code in the dictionary, we output the corresponding code to the compressed output and add a new code to the dictionary for the current sequence of characters after we have outputted the code for the matching sequence. We add this new code to the dictionary for the current sequence of characters. So the next time which we receive the same sequence, we can simply use it. So this is the one key core aspect of the LZW algorithm, which reduce, which is very useful when there is redundant data. So we repeat these steps until we process the entire input, and we continue to process this until we have read all the input data and compress it into a series of codes. Overall, LZW compression algorithm is powerful tool for lossless data compression. By identifying repeated patterns of characters in our input data and replacing them with shorter codes, we can significantly reduce the size of our files without losing any information. With its ability to achieve high compression ratios and low memory requirements, the LZW algorithm is widely used and can be applied for a variety of data types and applications.
We use the above mentioned pseudocode to create a CLI utility, which is implemented using Java. We used 8 bits to 12 bits to uniquely represent the frequent pattern to be stored in the dictionary. Here you can see that we are using the jar file. This jar file is also submitted with a final submission. You can execute it by running java-jar jar file name. The CLI utility will prompt for the option whether to compress or decompress. In this example, we have compressed the file called text.txt. Yeah, we have mentioned the file path. And once we execute it, it will provide us a compress the file with .lzw extension. This extension is just for identification. It's not mandatory. Similarly, for decompression, we will be providing decompress option, and we will provide the compress the file with .lzw extension, and it will decompress and provide us the original file. Now let's see how much it has compressed. As you can see, the original file was around 16 KB, and the compressed version is around 4 KB. This is because this file has a lot of redundant content, and as we know, like LZW is very good compression algorithm for the redundant content. Moving on to the conclusion, we have learned how LZW compression works, how it's different from Huffman encoding, how LZW is good for redundant data while Huffman is good for characters with high frequency. We had a great time working in this project together, and we explored a lot. Thank you.